Let me start by saying again that I'm happy to be here. I think the title that Wolfgang, with my broken German, this is what he said I'm going to talk about. So I'm going to talk about cosmic rays and its implications to the understanding of climate change. Given that Professor Svensmark is here going to talk about cosmic rays, I'm going to concentrate on the solar climate link. So I'm going to show you the evidence that the sun has a large effect on climate and how this affects our understanding of climate change over the 20th century, over the 21st century, and so on. Okay, so if you fall asleep after lunch, I'm lucky, I'm giving you this presentation, so I cannot fall asleep. But if you fall asleep, just remember these points so that if you ask later, if you're asked what am I going to talk about, these are the points to take home. First, the sun has a very large effect on climate. The effect is much larger than what you would expect from just changes in the solar irradiance, which means that there must be an amplification mechanism. The IPCC, or say the mainstream climatology, ignores this, the evidence for this. They ignore the fact that the sun has a large effect on climate. Now, by doing it, they think that climate sensitivity has to be on the large side, and as a consequence, they also predict that the 21st century temperature warming is going to be much larger than what it is going to be for, say, a business as usual scenario. If you're wondering, just a second, I'm coming here and giving a different story than what the standard paradigm is. How does it stand in comparison with the standard picture, or say what's wrong with the standard picture, so that you'll realize that there's nothing inconsistent with what I say and the data. So I'll show you that the IPCC does not support the standard picture, and that more importantly, it actually ignores data which would have otherwise forced them to change the standard law. Okay, so the first point, the sun has a large effect on climate. So to begin with, there are many correlations showing you that the sun affects the climate. And what do I mean by solar variability? The sun is not a constant star. It doesn't emit constant amount of radiation. And more importantly, the non-thermal component of the sun, whether it be changes in the solar magnetic field, the number of sunspots, the solar wind, which is actually important because it affects the climate, the amount of UV and things like that, they change with the solar cycle. Every 11 years or so, the north and southern poles of the sun switch, so we have a quasi-periodic 11-year solar cycle, but on longer timescales we have secular variations in the solar activity, which also translates, as we'll see, to changes in climate. Okay, so the sun is not a constant star, and as we shall see, it affects the climate. I think this is one of the nicest correlations that you can see between solar activity and climate on Earth. We see here, this is by the way work by the Augusto Mangini group up the Neckar River in Heidelberg. So it's really local, but it's not that local because the data that you see here is a solar proxy at the top and a climate proxy at the bottom. At the top, we see carbon-14 to carbon, say, 12 isotope ratios as derived by tree rings all across the world. Carbon-14 is a cosmogenic isotope. It's formed in the top of the atmosphere by high-energy particles coming from outside the solar system, called cosmic rays. But these high-energy particles are modulated by solar activity, such that when the sun is more active and the solar wind is stronger, we get less cosmic rays reaching the Earth and less formation of carbon-14. So this basically is a proxy of solar activity. On the bottom, we have another isotope ratio. Here we see the ratio between oxygen 18 to oxygen 16 in stalagmites in a cave in Oman, in this case, which is a proxy of the temperature of the water in the Indian Ocean, which is where the water coming to the, falling as monsoon water in Oman, and later seeping through the ground and forming those nice stalagmites, or stalactites. As you can see, there is a very nice correlation. Can you see the correlation? Oh, you don't need glasses, that's good. Another example, here we have, again, carbon-14 is derived from tree rings in blue, and in black we have a measurement or some proxy of the climate in the northern Atlantic, showing you whether it was cold or warm. We see here the marine proxy is basically looking at annual layers in the cores drilled out of the seafloor. When it's colder, ice can drift on the sea and reach further south before it melts and leaves the ice-rafted debris on the ocean floor. Colder weather would allow glaciers to drift further south, and you will see it as dark layers of ice-rafted debris. So this is basically a proxy of the climate in the northern Atlantic. And again, you see a very nice correlation which demonstrates that the sun, as proxied by the carbon-14, affects the climate, in this case, northern Atlantic. Now, there are a lot of examples like that showing you that climate all over the Earth is affected by the sun. On the 11-year solar cycle, you see variations. In red, you see variations in the cosmic ray flux, which again are modulated by the solar activity. And in blue, you see variations in the low altitude cloud cover on Earth. I show this correlation because it's going to be the link to the next talk that you're going to hear, because this not only shows that the sun has an effect on the climate, it actually pinpoints or indicates what is the actual mechanism that does so. Okay, so we've seen that the sun has a large effect on climate, but the question is, can we quantify this effect? Maybe it's small and you don't have to take it into account. Maybe it's large and you have to take it into account. So can we quantify the solar climate effects? And the answer is yes. Here we see two graphs together. In red, you see the solar cycle. It's the solar constant reconstructed from various proxies. So you can see the 11-year solar cycle. Every 11 years or so, the sun is more active, and it translates, for example, to a slightly brighter sun. But in addition to that, in black, you see the rate of change of the sea level. When the sun is more active, you see that the oceans are expanding. The sea level is rising. Now, on short time scales, most of the sea level change is because of absorption of heat. Okay, so what you're doing here, you're measuring the flux or the incoming flux associated with the solar cycle. So you're using the oceans as a huge calorimeter to quantify the effect of the sun. Why is it important? It's important because it tells us that the sun has a large effect on the climate, and it tells us exactly how large it is. Okay, you can quantify, you can play this game of quantifying the solar forcing with different data sets. I've shown you the sea level change with tide gauges and with satellite altimetry. You can look at the amount of cloud cover which changes over the solar cycle, the previous graph I've showed you, and you can, using the satellite data, you can translate this change in cloud cover to a change in the radiative forcing, and you find this number. You can also look at the change of the sea surface temperature of the oceans, or the ocean heat content from buoy data over the past, say, 50 or 60 years. In all cases, you see that the radiative forcing associated with the solar cycle over the 11-year solar cycle is about 1 to 1.5 watts per square meter. Now, for comparison, if you just look at what is the change in the solar irradiance over this time scale, and you divide it over the surface of the Earth, you find that the solar forcing, just because of the change in the irradiance, the luminosity of the sun, is about 0.2 watts per square meter. Now, if you open the, the IPCC, the scientific report, they'll tell you, yeah, of course, we take the sun into account. But what they are actually doing, they're taking this effect into account. They're not taking the whole effect that the sun has on climate. We have seen that the sun has a large effect on climate. You can quantify it. And the big question is, why doesn't the IPCC scientific report take that into account? This thing was published in a peer-reviewed journal in 2008, so it satisfies all the criteria of what the IPCC should be looking at, but it's not there. I think that if they do take it into account, it will have to change their conclusions about what drives climate, or in particular, how large is climate sensitivity. Okay, so one of the reasons why they ignore it is because of the implications that the solar climate link has on the climate. So what are the implications? Now, a very crude way of looking at the climate response would be in this way. If we were trying to explain a 20th century temperature change with just as a response of climate drivers, then you have the mainly anthropogenic forcings to play with. And in order to explain the somewhat smaller than 1 degree temperature increase over the 20th century, you will need a high climate sensitivity. Okay? But this high climate sensitivity will necessarily translate into a high temperature increase over the 21st century for a given emission scenario. Now, if you have another positive forcing, in this case the sun, because the sun's activity increased over the 20th century, the combined forcing is going to be larger. So in order to explain the temperature increase that you have seen over the 20th century, you will now need a lower climate sensitivity. And with a lower climate sensitivity, you will get that the predictions for the 21st century temperature increase are going to be smaller as well. Okay, again, this is a very crude picture, but it underlines what is the main reason why, say, mainstream climatology is trying its best to ignore the solar climate effect. I'm also saying that it's very crude because there are other things which affect the temperature change. For example, natural variability, which I guess we're going to hear from Professor Linsen's talk. Okay, can you explain 20th century when the sun has an effect on climate? The answer is that you can explain the 20th century temperature change even better than when you exclude the effects of the sun. Here you have the results of a climate model which allows for the sun to have a large effect on the climate. In fact, it allows it to have an effect with a free parameter, and the fit finds also what this parameter is, and lo and behold, the best estimate for what the sun has been doing over the 20th century agrees with what we measure with the oceans that it does. Now this fit, when you do this fit, you find a residual between observations and model, which is twice smaller than what you would expect or what you get from global circulation models, which excludes the real effect that the sun has. Okay, you can use this model. This model assumes radiative forcings or standard radiative forcings that we have imposed on the climate, and then you can integrate it forward in time for the parameters that fit the 20th century. And when you do that many times, you can get a prediction for what the temperature increase over the 21st century is going to be under a business as usual scenario. For comparison, these are the scenarios of the IPCC. We have seen that if you take into account the sun, then you have to change your perception of what the climate has been doing, or various things about the climate. But then you can ask the question, just a second, every day I hear the IPCC coming out with a story. What's wrong with this story? I mean, how can I compare this story to what I'm telling you? There's no empirical evidence showing you that CO2 must have a large effect on the climate. And the other thing is that there's no empirical evidence that the climate sensitivity has to be large, which is what they assume when fitting the 20th century and predicting 21st century climate change. And an example for the fact that there's no evidence for CO2 affecting the climate is this graph that we have seen featured in Al Gore's science fiction movie. You see here a reconstruction of the CO2 from ice cores, in this case in Antarctica. And on the top in the red line, you see a reconstruction of the temperature on Earth. Now you see that there's a very nice correlation, right? Okay? You don't need glasses, it's okay, you see it. Okay, so Al Gore in the movie, he says there's a very complicated relations, but you see that when there's more CO2 in the atmosphere, the temperature is higher, because he wants to make us think that this is evidence demonstrating that a large amount of CO2 in the atmosphere necessarily causes an increase in the temperature. What he didn't tell us is that CO2 generally lags variations in the temperature. So Although CO2 should have some effect on the climate, this graph that Al Gore has shown us doesn't indicate anything in that direction. It just tells us that there's a very nice equilibrium between CO2 which is in the atmosphere and CO2 which is dissolved in the oceans or undergoing some chemical equilibrium in the oceans. And this equilibrium between CO2 in the oceans and CO2 in the atmosphere depends on the temperature, such that when you hit the oceans, you release more CO2, which is why the CO2 generally lags behind the temperature. Okay, so this is a very interesting graph, but it tells you nothing about the effects of CO2 on the climate. There's also no evidence that the climate sensitivity has to be large. The claims that the climate sensitivity has to be somewhere between 1.5 to 4.5 degree increase for doubling the amount of CO2 all originate from climate models. People run global circulation models, and they get responses, say, in this range, and then they say, okay, so we think that the climate sensitivity is in this range. What they don't tell you is that the climate models are actually very bad in predicting the climate sensitivity. And the reason they are very bad in predicting the climate sensitivity is because of, in particular, one feedback. If we increase the radiative forcing, so suppose we put some CO2 in the atmosphere, we will block some of the infrared going out into space. And in order to balance the radiation going back into space with the radiation that we get from the sun, the temperature at the surface has to increase. But in addition to this direct effect, if we increase the surface of the temperature, we're going to evaporate more water. So the atmosphere is going to be more opaque because of the water. So that's a positive feedback. But in addition to the water vapor in the atmosphere, we're also going to have more clouds. And the clouds can do a lot of things. They can cool, they can warm. And in fact, nobody knows by how much the clouds are going to change. And all the global circulation models essentially treat clouds with recipes. Okay, they tell us, or you put into the global circulation model, by how much the clouds are going to change if you change the water vapor by a given amount or the temperature by a given amount. And this graph here, this graph here demonstrates that the cloud cover is the dominant uncertainty. This graph, incidentally, is from 1989. Quite bizarrely, things didn't change that much since then. You see here a bunch of climate models, and this here is the sensitivity or equilibrium sensitivity of the climate model by how much the temperature is going to change if you double the amount of CO2 as a function of the feedback that the model has through cloud cover. This basically depends on the recipe that you put in order to describe the clouds. And you see that all the climate models resides close to a line, which tells us that this is the dominant parameter affecting the climate sensitivity. Since we don't know this, we don't know this. Okay, so basically, global circulation models are bad in predicting climate change. Okay, then there's a problem with the IPCC evidence. We are told that we have evidence proving that humans are the cause of global warming over the 20th century. What is this evidence? In quotation marks, because it's not real evidence. There are two main arguments. The first argument is that you cannot explain the 20th century without anthropogenic greenhouse gases. The other argument is that the 20th century warming is unique. And if it's unique, then it's probably human. But both arguments have loopholes. Well, first, this is from the fourth assessment report. We see here a fit between the temperature increase, observed the temperature increase in black, and model fits to it. And these are models which include the anthropogenic forcings, and this is the result of climate models which exclude the anthropogenic forcings. And you see that you cannot explain the 20th century warming if you exclude the anthropogenic forcing, right? Wrong. Why is it wrong? It's wrong because we have seen that there is another climate driver, and that's the effect that the sun has on climate. Okay, they don't take it into account. Okay, the other thing is the temperature increase over the 20th century is not unique, and the thing that you need to do in order to see why is to just Google ClimateGate and realize that the graph that was used in order to demonstrate that it's unique is I don't know how to describe it better. What?
Fabricated.
Religious Jews are not supposed to mix things which are not of the same kind, like wool and cotton, because one comes from animals and one comes from plants. It's called shatnez, and this is exactly that. Okay. So we've seen that the evidence doesn't support the IPCC picture, but it's more than that. The evidence contradicts the IPCC picture. There's evidence that the effect of CO2 on the climate is small, and there's empirical evidence that shows us that the climate is not sensitive. And I'll show you a few examples. Here you see a reconstruction of the global temperature over the past 500 million years. Okay? It's from oxygen 18 to oxygen 16 isotope ratios, and it was carried out by my colleague, Professor Veizer. At the top, you see a reconstruction of the CO2 levels in the atmosphere at the same period, over the same period. For example, 450 million years ago, we see that the CO2 levels in the atmosphere were about 10 times larger, this is a logarithmic scale, 10 times larger than what they are today. On the other hand, the amount of glaciations that we had during that period was more extensive than what we have today. Okay, so you can use this lack of correlation between the CO2 and the temperature to place an upper limit on the effects of CO2 on the atmosphere. And lo and behold, the upper limit that you get from it is that if you double the amount of CO2, the temperature shouldn't increase by more than 1.5 degrees, which is exactly the lower range of the IPCC. Another example for a discrepancy is since the first IPCC report, actually since the Charney report from 1979, the claimed climate sensitivity range was 1.5 to 4.5 degrees, except for the fourth assessment report where they changed it, but they returned it back in the last report. This means that the predictions which were made in the first assessment report of the IPCC should have been valid. The temperature on Earth should have increased within this range of predictions. But what has the temperature on Earth done? The temperature on Earth is now, actually this is from 2 years ago, it continued to below the range of predictions. So any decent theory which made predictions, when the predictions are not satisfied, they go back and say, okay, we have to update the theory, we now understand better, we should change the predictions. But this is not what happens with the IPCC. What happens with the IPCC is that every 6 years they reset the predictions clock, and by definition we're always within the range of predictions. Alarmists ignore the fact that the sun has an effect on the climate because it implies that climate change is going to be much more benign than what we hear. So how do they manage to ignore it? Well, the first thing I mentioned, they just avoid mentioning it. The fifth assessment report doesn't include measurements or quantifications of the solar forcing. There are other claims that claim that there is no solar climate link. They simply claim that it's wrong, and I'll give you one example. And then they also claim that without a mechanism, it cannot be considered seriously. Okay, so here is an example for someone claiming that there's no solar effect. Recently, say in the past year or two, came out the Berkeley temperature reconstruction of Earth, the best temperature reconstruction. It's not that they're the best, it's just the acronym is the best, that's all. And they claimed in one of the follow-up papers that they don't see any solar effect So the sun is not affecting the climate, or it has a minor effect on the climate. And why is that? It's very simple. What they try to do, they try to correlate the predicted temperature, assuming that it is some response of the CO2 and some response of the solar activity, and compare it to the observed temperature. Now, what they didn't take into account when they did this annual comparison is that climate is a low-pass filter, which means that a 1 watt per square meter response on a few-year timescale is much smaller than a 1 watt per square meter response on a centennial timescale. And such a simple comparison necessarily kills the solar effect because you don't see a large temperature increase over the 11-year solar cycle because of the low-pass filter effect of the climate. Then they also said, let's not look at annual data, let us look at decadally average data. But when you look at decadally average data and you throw away the data that's basically the 11-year solar cycle, over the 20th century you have the anthropogenic forcings which increased, and you have also the solar activity which increased almost monotonically. So when you do that, you actually cannot differentiate between the two effects, and the lower limit that they put on the solar effect when they do this kind of a comparison actually includes the real number. So they didn't prove that the sun doesn't have an effect on climate. We know now with a lot of empirical evidence that we'll see in the next talk that the sun affects the climate through modulation of the cosmic rays. Okay, so just as a teaser, this is the effect. The sun, which has a solar wind, we know that from comets, for example, we see cometary tails, we can see aurorae. This solar wind modulates the flux of high-energy particles which come from outside the solar system. They actually come from the death of massive stars. These high-energy particles are the dominant source of ions in the atmosphere, such that when the sun is more active, we get less cosmic rays and less ionization. We therefore get eventually less growth of cloud condensation nuclei, which are particles needed in order to condense water vapor and form cloud droplets. So you change the characteristics of the clouds, you make them less white when you get a stronger solar wind, less cosmic rays, less cloud condensation nuclei, droplets or clouds which are less white, so you reflect less of the sunlight and increase the temperature. So in fact, there is a mechanism, and we have a lot of empirical evidence to suggest that it exists, which means that you must take the sun into account. Okay, so let me summarize. There's a very large solar climate effect, and we can quantify it. If you take it into account, you have to change your perception of what climate change has been over the 20th century and what climate sensitivity is. What it has been on the 20th century and what it will be in the 21st century. And it will still be ignored by the climate community because it's hard for them to take it into account. And I think I will end with this really succinct summary, which tells us the following. I'm quoting Al Gore, quoting Mark Twain, who said that what gets us into trouble is not what we don't know, it's what we know for sure that just ain't so.